Hi, in this video, we want to take a look at how much influence one data point can have on our linear model. All right, so for this example, we're going to take a data set and we're going to change one value in the target variable on one data point. And we're going to see how does that change the data? How does that change the regression model that we have? Okay, so what we're going to do is that we're going to take a particular data set. So here we're going to call this a Huber data set. Here are the predictor variable values. So put it this way. All right, so X is the predictor variable. Now over here, if you see the Y good, here are the Y values, the target variable values. Now, everything for Y bad is the same as Y good all the way down the line until we get to the very bottom. Notice that instead of having negative 11.4, we have 0. All right, one value is changed in the data set. Now, this is a very small data set, so realistically, we probably wouldn't have this extreme of an issue as what I'm going to show you today, but this is an extreme example to help drive the point across how having like a bad observation in your data set will throw off your model to some degree. And here, this example is to give you like a severe case. Now, this is a very small data set. If we're in the situation where getting like 6 observations is very expensive, or it's something that's very rare, a very rare event, then this could be an issue that we run into realistically when one observation is very difficult or expensive to obtain. All right, so let's go ahead and build the model. So what we're going to do, I'm going to use the LM function for linear model once again. Specify the formula. So Y bad depends on X, and my data set is Huber data. So my convention for output is always the function and then something that describes what's going on, usually the data that I'm applying it to. So LM Y bad. For LM Y good, I do something very similar, except my formula, I'm saying that Y good is now the target variable, and it depends on X. Okay. So let's see what happens. So let's take a look at the summary of the models. First and foremost, let's take a look at the residuals. 2.4, negative 0.3, negative 1.6, negative 1.4, and then 0.7. Okay. All right. So then this is, when we have, that's for the bad case. Okay. So what is it when we look at good? Well, instead of like 2, we have 0.5. And instead of 0.4, we have 0.3. Instead of 0.3, we have 0.1. Negative 1.6, and then 0.6. So, we can see that generally the residuals are smaller in the good version. Okay. Now let's take a look at the coefficients. Let's look at the difference in them. All right, so in the bad case, the intercept is, less than 0.1, and the slope is negative 0.1. And then here on the good, I have 1.8 and negative 1 for my intercept, or for my coefficients. That's a pretty big difference off those two values. And let's look at the standard error. How much bigger is the standard error on these? Wow, look at this, 0.6, 0.2, 0.1, 0.04. This is a big difference in the standard errors. And correspondingly, our t-values, which are going to be the ratio of estimate and standard errors, give us what we would expect to see, is that here neither one of these are statistically significant, while here both of them are statistically significant. All right, we can see that changing that one Y value has had a huge impact on the model so far. But wait, there's more. Because if I start looking at the multiple R squared, adjusted R squared, those are lousy. That's nothing. If I look at the R squared down here, of course, it's on the next page. It's 0.99. Like, wow. That's Yeah, that's a pretty big difference. And we can see that here the p-value is not statistically significant for the f-test, while down here in the good version, that's very significant. So huge difference, huge. All right, so now that kind of gives us like the hypothesis testing point of view, so we can see like the numbers spit out at us. I kind of just vomited the numbers onto the page, and we can see the difference. Now let's actually plot it. So what I'm going to do to plot, I'm going to make a scatter plot, with the x and the y variables. Now on this line, I'm setting up what the limit of the y values are to make sure that the vertical scale on the scatter plot is the same on both of them. So since I changed the y coordinate on one of the data sets, they're going to have different y value ranges. So I want to do an apples to apples visual comparison. So I'm saying that the scale on y has to be the same. Now on x, the x variable is the same because we're using the same predictor variables. So I don't need to worry about that. Now PCH is the plot character. I put 19 because I want solid. And then I find that steel blue works pretty well for printing. So I tend to go steel blue. So let's look at this. All right, so here, that kind of looks like a straight line. But over here, this is like way off from everything else. So previously, this would have been like down here in y good, but it got bumped up here. So we can see that the curve wants to follow this. The straight line wants to follow this, but this one point is pulling the entire model up. All right, so something that you're going to find out as we work through this course is that the points that have the x coordinates that are farther away from the mean of the x values are going to fundamentally have more influence on the data points than the points that are close to the mean. And so this is pretty far off from the mean of the entire x values. Therefore, this has a lot of influence proportionally compared to the rest. So it's pulling hard. All right, so now let's do the same plot, but now it's going to be for the good version of the data. So I'm taking the x coordinates, and then y good is my y coordinates. I'm using the same scale as the previous. Solid is plot character 19, and then steel blue. Oh, and I forgot to mention, when I do AB line, to specify a line, either I can say that the intercept is A, the slope is B, and that will give me a line, or I can say a regression object is where we get the model from. So if I say reg equals a regression model, I'm telling R to grab the straight line from the regression model. And here, when we look at y good, we can see that's a straight line. It's looking pretty good. Now, you'll notice that this point does have a lot of influence on it because it's going, like, the line is going like nearly perfectly straight through the middle of that point. It's not perfectly going through there because there is influence over here, but it's pretty close. And the reason why it has so much influence is because 10 is so far away from the average of all of the x coordinates. All right, so now let's go ahead and take a look at the influence of each point in the model. There's something called the hat matrix that we will be looking at later. Now, the diagonals of the hat matrix evaluate the influence of each data point, but there's a catch. In ordinary least squares regression or weighted least squares regression, what's going to happen is only the x coordinate has influence. And so it works out that in general, the points that are farthest from the central tendency will have more influence. And so because with ordinary least squares, only the x coordinate determines the leverage. So the diagonal of the hat matrix gives us the leverage of each data point. And the leverage is determined only by the x value in ordinary least squares. So the leverage measurement is not going to help us on this problem because I only changed the y coordinates. Now, something about the calculations with this is that when I look at the influence, there's going to be a whole bunch of different coefficients. How that works out, actually, I'll go ahead and scroll down. All right, so here is the leverage of each data point. And you'll notice that in the bad version, it's 0.94. But also, if I look at the good version, it's 0.94. We have the same value both times. That's because leverage only uses the x coordinates in ordinary least squares. Now for the coefficients, what's going on here is that they build the model, R builds a model, R removes that point, builds the model again, and checks how do the coefficients change. So when 1 was removed, this is how much the coefficients changed. When 2 was removed, but the other data points were kept, that's how much the coefficients change. If I look at the, this is in scientific notation, so -2, -2, -3, -2, -18, here it's practically nothing. And you'll notice at this point is going to be probably the closest to the central tendency for the x values. Now here, that's the scientific notation, the exponent is -1. That means that this one has the most influence. And so that's one of the impacts of this, is that one data point has the most impact on the coefficients because we have the biggest change here. Now the sigma here is a standard deviation of the residuals when I remove that one, remove that one data point. So here, the standard deviation of the residuals when the first data point was removed was 1.8, and then the standard deviation was 1.8 when I remove the second data point, and so on. Now you can see that the moment we take the sixth data point out, that's the one that I changed, the standard deviation of the residuals dropped. All right, so remember, for hypothesis testing, we do not like standard deviation. We want it to be teeny tiny and small. So here, because standard deviation corresponds to the precision of our measurements. We like precision, we want standard deviation to be small. And we're not going to talk about the weighted residuals at this time. Now, when I go down here and I start looking at the change when we use y good, here the exponent is -1. Down here, it's -2. So we have an order of magnitude smaller. Also, the coefficient is 9. Here, the coefficient is about 2. I mean, that's we've got a big difference. Now let's look at the sigma change. Well, so here, when I don't have the sixth data point in there, we can see that the standard deviation of the residuals are all pretty small. They're all much smaller than they were in the bad version. All right, so when I take a look at the y-bad scatter plot, you might go, hey, you know what? I think I should put a quadratic here, a degree 2 polynomial through this. And that if this was the data that was handed to you and you didn't know that this was an erroneous data point, that would be something that would be very reasonable to do. So let's go ahead and take a look at the impact of adding a degree 2 term to our model. All right, so to do a degree 2 model, degree 2 term, we have to use the identity function, and then we put our variable to the power of 2, identity variable to the power of 2, and then we put that in our formula, and then we just run it as like we do previously. And so we go ahead and do that. We do one for y bad and y good. Now, something I want to point out, when I look at the y good scatter plot, that's along a straight line. If it's close to a straight line, the quadratic's probably not going to help me out. And we're going to see the quadratic doesn't do anything for y good, but it changes a lot of stuff for y bad. All right, so here with y bad, we have statistical significance all the way across. Everything's less than 0.1. And we can see that our r squared jumped up. Now, remember that we're in the situation where that one data point had an incorrect entry. And since it was an incorrect entry, like if this was real data, I was working on this, I might not know it. And I might be building this model and be like, hey, a quadratic fits really great, when in reality, I should have a straight line and I should throw out that one data point and I wouldn't know it. Remember, whenever we're using data, we don't actually know what's going on. We're using data because we don't know. That is fundamental to statistics. Now let's look at Y good quadratic model. And you can see that it's saying the p-value is big. It's saying that the quadratic term is not statistically significant. So this is implying to us that we do not want the quadratic term. We want to stick with the straight line that we had previously. All right, now let's go ahead and plot all four models. So here we just plot a model, or so we plot the data here. So I use the plot to get the original, like to get Y bad down, and then to get Y good, to get that one data point that changed, I went ahead and basically what this is doing, the points, I'm stacking this X and Y data on top of this plot. Well, it's the same data except that one point. So for everything except that one point, visually to me, it doesn't make a difference. I just see that additional point was put on there. Now for AB line, I'm just taking the regression models. Now, when it comes to the quadratic models, R really doesn't support quadratic models that well, honestly. That should be a sign that they're really not that used. They're not used that often in real life, by the way. If you look through textbooks talk about like quadratic regression and degree 2 terms and cubic splines and all this stuff. And yeah, this stuff is kind of used, but really in regression, we almost always keep it to straight lines. There's reasons for that involving like Taylor polynomial theory and stuff like that. But most of the time, we do not bother with degree 2 terms in real life, in real modeling. It gets talked about a lot in your statistics classes. It gets talked about a lot in psychology classes. I had a psychology professor. I double majored in psych, by the way. That just went on and on about it. But now that I'm modeling, I don't do it. I've yet to use a quadratic model. There are other things to use. But before we get to that point, we're going to use degree 2 terms because it's simpler algebraically and it's more of a bridge to other concepts. So to be able to plot with the degree 2 models, I have to use a prediction. I have to do the predict function. To be able to make a prediction, I have to have new data to put in. So I go ahead and create a scoring data set. All right, training data, you build the data on. Validation data, you choose your model. Test set gives you your honest estimate of performance. Scoring data is the data you predict on. So if you go into machine learning, you're going to need to know those 4 terms. For us, we've got training and scoring. Training is the data that we built on. That's the data we have so far. Score data is the data we predict on, which I just built right here. All right, now we use the predict function to make our predictions. So the object is the model that we're predicting with, and the new data is the data that we're making prediction on. And I'm using the lines function to go ahead and print those predicted values. And now I'm going to go ahead and make a legend. I'm going to put the legend in the bottom left, and I'm coloring them red, orange, blue, purple. I just can't pick those colors. There's plenty of different colors you could use. And then this is the order of the models in the legend, and I'm specifying that I want it to print lines instead of dots. So I put LWD equals 1, that's line width. And so when I look here, I can see that the Y good model, it's the same practically whether I have the quadratic or not. That's a sign I do not need the quadratic term in there. Now, for the Y bad, I can see that red is linear. Red is nowhere near these dots. But when I look at the quadratic fit pretty well. So if that was a good data set, but it's not, if it was a good data set, the quadratic model on Y bad would be a good model. So what do we need to take away with this? I need to have data quality before I start modeling. Data quality is super important. All right. Whenever you're doing statistics, whenever you're doing data analytics, anything with data, everything you do, the earlier you do something, the more important it is. Okay, so when it comes to my data, and when I go through, if I have a mistake in my data and I proceed, I don't know that there's a mistake in my data, what's going to happen is everything that comes later after that is going to have that error like built into it, and that error is going to propagate through the process. So it is absolutely critical that you have good data. A good rule of thumb is the earlier it is in the process, the more important it is. So just always remember that. Whenever you go like YouTube and you go to like machine learning classes and machine learning YouTube videos and stuff like that, they're going to emphasize the late stuff. Why? Because that is sexy. It is fun. It's interesting. You know what? It's not important. The stuff that is important is the early aspects of machine learning, the early aspects of hypothesis testing, early aspects of modeling. It doesn't matter what it is. The earlier the step is, the more important it is, because any mistake or poor choice that you make propagates through all of the other steps that you make. So that's something to always be mindful about. So if you need to commit more time and effort onto something in a project that involves data collection, and your experimental design, designing how you're going to collect the data, and the data collection process are absolutely the most important. All right, that's all I've got for you. Stay safe and take care.